Alright, hello everyone, welcome back. So in the last class, we have provided a very brief introduction for the query processing already, and we cover some basic information for logical and physical operators, if you still remember, right? And we also introduce what is the query execution plans. It is based on logical tree, and we also cover how to implement the choice at every node with the algorithm. Normally, the operation at each node inside the logical tree is based on three functions: the open, the get next, as well as the close, right? We also provide you with the example for the query processing, and we also mention how to define the three functions, the open, the get next, as well as the close functions for all the nodes inside the tree, and also how to define the algorithm to do the operation in the whole tree, right? The parent node can call the children nodes for open, for get next, and for close, right? Besides this, we also provide you with a brief introduction for the some basic parameters we may need to use in the following pages of the slides. So if you still remember, in the last class, we have mentioned 4 different parameters. The first one is a capital M, right? Normally, the capital M, we use M to denote the number of blocks that fit in the memory. It will be very important because, in the following pages, when we are doing some algorithms, we may need to unload the data into memory, and the general cost for processing some of the operations, they will be dependent on the size of memory, for holding the blocks, and this M can be used. Another parameter is a capital B on R. This R is a relation, right? And this BR denotes the number of blocks holding a relation. We can load all the data in the relation into the memory, and it denotes how many blocks we can use for holding the relation. And we also have a TR, right? This also, this R is also a relation. The TR denotes the number of tuples inside the relation. It denotes how many rows are there in the relation for holding the data, right? And we also have this VRA. It denotes the number of distinct values for the attribute A inside the relation R. So it can be very useful for calculating the following time cost for processing some operators in the logical tree. We will use all these 4 parameters in the following pages, and you can write down them on your paper when you are going over the lectures. So because we may use them very frequently, you need to know the physical meanings of these notations clearly in the following pages. If you still remember, we also mentioned the classification of algorithms in the last class. We mentioned some of the operators can be implemented with a one-pass algorithm. In other words, we can read data from disk to the memory only once, and then we can work only on the memory instead. Every operations will be on the memory, and we have nothing to do with the disk anymore. It is called one-pass algorithm. And we also have mentioned some exceptions like projection and selection. We will mention later why there are exceptions. And we also have a two-pass algorithms. We can read data from disk twice and work for the data which cannot fit in the memory, but not for the largest imaginable data actually. And we also provide you with some examples like sorting-based algorithms as well as hash-based algorithms. So for the data which are very large, we can use this multi-pass algorithm instead. In other words, we can read the data 3 or more times, and these algorithms are natural, recursive, and generalizations of the two-pass algorithms. Normally, it works without limit on the size of data. So the algorithm, to use for all the operations, all the operators in the following pages, it really depends on the size of both the data as well as the memory. If the data is not very large, then we can use one-pass algorithm. It will be very efficient. We can all load all the data into the memory. If the data is very large, however, the memory is not very big enough to hold the whole data set, then we can probably use this two-pass or the multi-pass algorithm instead. We will show you with some concrete examples for this one-pass, two-pass, and multi-pass algorithms in the following pages to implement the operators like projection, selection, sorting, hash-based algorithms. Okay, so this is what we have covered in the last class. Then today we will move to the concrete algorithms we can implement these operators we mentioned before. If you still remember, before we have one example on the tree, right, for the scanning of the data. If you still remember, we show the example again for you here. So we show you with the example for the query, right? We can define one logic tree for the query, and for the different nodes, they are based on the scanning of the purchase table as well as the person table. It covers both the table contents as well as the index tables, right? By scanning these kinds of tables, we can load data into, either memory or some other space for operations, right? So the table scanning can be very important. It is also the initial step for processing on this logical tree. And then in the following pages, the first algorithm we plan to discuss about is called the scanning of tables. What will be the time cost for scanning one table? It really depends on the index table we are using here actually. So if you still remember, right, before when we are talking about the index tables, we mentioned two different kinds of index tables. The first one is that this table is clustered, right? The clustered versus unclustered. So if the table we plan to scan is clustered, in other words, these blocks will consist of only the records from this table. So these blocks kinds of sorted according to the records orders, right? If so, then we can do the scanning in a very efficient way, actually. So if the table is clustered and the table scanning, of the whole relation table, if we know where the block is, and then we can do the scanning in a very fast manner, the time cost will be based on the BR. If you still remember BR, right? BR denoting the number of blocks for holding the relation. Because we know this table is clustered, in other words, we just need to locate the blocks where the records comes from in the table. In other words, we just need to locate the blocks. Time cost will be about BR, right? And when we are doing the index scanning, we just check the index tables, and if we also have the index to find the blocks, then time cost will also be based on the BR, right? It is based on the time cost for finding the blocks. If we locate the blocks, then we can find the records very efficiently because it is clustered. On the other hand, if the table is unclustered, in other words, its records are placed on blocks with other tables. In other words, we have to scan all the tuples, all the records, so we will be able to find the target record we plan to locate, right? So we may need to have the one reading for each of the blocks in our tables, right? And the time cost will be based on TR, right? If you still remember TR denotes the number of tuples in the relation R, right? So you can see the difference. If the table is clustered, in other words, it is sorted, we just need to find a block, and then we can find the record very efficiently. And the time cost will be based on the time cost we spend on locating the blocks. It will be about BR, right? The number of blocks. However, if the table is unclustered and its records are not sorted according to the blocks actually, and we have to scan all the tuples, so we'll be able to find the target record, and the time cost will be about TR, the number of tuples in the relation R. So this is for scanning other operation we show in the previous logic tree. Besides scanning, we also need to do many other operations, right? Like selection, projection, and we will show its time cost in the following pages.